Welcome back, ladies and gentlemen. To start off this video, I want to talk about what we learned last time. What we learned last time is how a particle is affected when it enters into a magnetic field. Now we're going to have to make a few assumptions. The first one is that my lines of the magnetic field are perpendicular to the motion of my positive particle. The second one is that when this particle goes through, it's going to go through directly through these parallel lines. All right, it doesn't go through the outer edge, it doesn't go through the top edge. So after we've kind of established that, I want to say, what's the force going to act on this? And if we remember our right-hand rule, we have our B field lines pointing kind of horizontally. We also have the velocity of our particle, which I'm going to assume is going mostly into the board. All right? So if I have my velocity vector going into the board, I have my magnetic field lines pointing horizontally, the force then should be acting in the downwards direction. Now, the second part I want to say is, what happens if I had a stream of particles, something that looked like this, where now I have a lot of particles all going in the same direction, entering into the same magnetic field? Wouldn't it be logical to say that each one of these is going to experience the same force? So now, what would happen if I were to encase these in a tube, where now I have all of my positively charged particles moving into a magnetic field surrounded by some casing? What kind of connection can we make with a charged particle moving in a tube? Now, hopefully, what you thought was of current, because current is the flow of electrons, right? And if we think about the direction of the current here, we've got our positive end on this side, our current would be flowing in that direction. As it comes around, it'll be going through the magnetic field. So now I've got my flow of positive charged particles going through the magnetic field, and I've got my magnetic field still in the same direction. The force that this wire would feel would be in a downwards direction. So that's a bit of an extrapolation of what we talked about last time. So Mr. G, what you're saying is you're saying that current in a magnetic field experiences a force, but we didn't have that in our first equation. Why is it that force is equal to charge times velocity multiplied by the B field has nothing to do with current? Well, in actuality, it does. And what we can do, let's write out what our units are for all of these. What are our units for charge, for velocity, for our B field, for our force? All right, so we got newtons is equal to coulombs times meters per second multiplied by Tesla. And again, I don't see where current comes in. Well, tell me, what is current? What exactly is the definition of current? What does it mean? Well, current is the flow of the electrons, but when we look at it, it's counting the number of electrons. Because when we had our split, our junction, when we thought about current flowing through a wire and it hit a junction, if I had one current of amps going in, 1 amp of current going in, and I had 0.25 going off the top, I knew that 0.75 was going to have to go down because it's the number of electrons going through, and I couldn't have a loss of electrons or a gain of electrons, so it's counting the number of electrons. Okay, so the number of electrons would be something like, if I have 1 electron, I would have 1.6 times 10 to the negative 19th coulombs, or if I had 10 electrons, I'd have 1.6 times 10 to the negative 18th coulombs. So the number of electrons would give me how much charge there is, but what's the difference between having, let's say, 1,000 electrons going through a wire in 1 minute, or 1,000 electrons going through a wire in 10 seconds? I guess thinking about it in terms of an ammeter, and what an ammeter does, and it counts the charge it goes through in a given amount of time. If I have 1,000 electrons that go through in 1 minute, as opposed to 1,000 electrons going through in 10 seconds, then that would mean that the 1,000 in 10 seconds would have to be moving faster through there. So you're telling me the amount of charge multiplied by how fast it moves through there, depending on how much speed they have when they go through there. If I have 1,000 electrons going through in 10 seconds, they have to be moving a lot quicker than if it takes them 1 minute to go through. Now, let's rewrite this in terms of thinking about current. Okay, thinking back on it, current was equal to the amount of charge going through a given space per second. So I put the charge per second, we were talking about the current flowing through the wire, and it also depended on how fast it was going through, meters per second multiplied by my Tesla. So coulombs per second multiplied by meters per second times Teslas gives me my newtons, right? Well, not exactly. Yes, I agree here. Coulombs per second is the measure of current. But if we put that just directly into here, it's no longer charge. I've now made it charge over a given unit of time. So if you put that in there, we've changed around our entire equation. It's no longer a value of force that we would get. So we have to find some way to rearrange this. And what I want to go to is I'm going to put in a little math example. And my math example is going to be 5 multiplied by 3 over 2. And that should give me a value of 7.5, right? 5 times 3 gives me 15. 15 divided by 2 gives me 7.5. Could I also rewrite this as 5 over 2 multiplied by 3? Because half of 5 is 2.5. 2.5 times 3 should give me 7.5. So these two equations are synonymous. Now, if we think about these in terms of variables as opposed to numbers, I do want to say coulombs per second, the amount of charge per given amount of time, is current. I like this part. But where did that second come from? Well, another place it could have come from was at meters per second. Now, these two equations are synonymous. If I were to say charge multiplied by velocity is the same as saying coulombs per second multiplied by distance. Both of them multiplied by a B field. So then what would our equation be in terms of, let's think about variables as opposed to units. Alright, so then we have force, we turn this into current, and we still have our B field. The M, what is that going to turn into? We can turn into distance, value of x, how long it's in there for. But that just looks funny, putting an x and an x next to each other. I don't think that that would make much sense. So I guess looking at my formula sheet, the options that I have would be force and current, and B would give me a value with length. So force is equal to current times the length of my wire in the B field. That's fantastic work. Now, the only thing that I wanted to add on to that was that it is dependent on the angle. Remember, if I have my B field pointing to the left, I have my current flowing to the left, or my particle moving to the left or to the right, those two directions are in the same, they're parallel with each other. So the difference in my angle would be 0. So the force that it would feel would also be 0. But if I have my B fields pointing horizontally, and then I have my current going either up, down, into the board, or out of the board, we would get the maximum amount of force. And depending on how much deflects from that B field is going to depend on how much force there is. But we get the maximum when our sine theta is at 90, or we multiply it by 1. Now this is where we get our SI units for Tesla. In the last video we solved for B, and we ended up getting these funky units. But now what you can do is you can tell me what the SI units are for the Tesla. Mr. G, why do you make this stuff so easy? So I rearranged, and I got force on top, I got my current on bottom, and I've got my length on bottom. After I rearranged, we measure force in newtons, we measure current in amps, and we measure length in meters. So it's newtons over amps times meters. Simple. Well, you are right, I do make this too easy for you, but because I made it easy doesn't mean you should just underthink it. What do we measure newtons in? Well, newtons is the same as mass times acceleration, and then if I have amps over amps times meters, do we have units that can still cancel? They didn't say how far I had to simplify it, but I can take out my meters, so I'd have kilograms over amps times seconds squared. So we got our B field. We measure that in Teslas. Teslas then are kilograms over amps times seconds squared. Okay, so now how is current then related to our B field? Or is there a relationship? Could I have a current without a magnetic field? Or could I have a magnetic field without a current? So I thought back to our very first example to talk about magnetic fields without a current. And our first example, we had a proton moving through here, but if there was no proton moving, then there would still be those field lines. So I guess with permanent magnets, there always will be a magnetic field. just like the Earth always has a magnetic field. We can validate it using a compass. Now, for how current and the magnetic field are related, I would say in order to keep force constant, as current goes up, the B field also goes up. So they would be directly related. Kind of. Yes, if we wanted to keep force constant, as current would go up, I would have to increase the amount of magnetic field, or the strength of the magnetic field. But if we were to talk about a current carrying wire in a magnetic field, because they are a cross product, they're independent of each other. I can have the current flowing horizontally, and I can have my B field flowing horizontally, and have the same strength field, or I could rotate it, where I would have my B field pointing horizontally, and my current flowing vertically. Now my force would change. But these two could be the same values. I could have my same value in Tesla as well as amps in two different orientations. I could have them going perpendicular or horizontal with each other. So they're actually independent of each other. Just like when we had a ball rolling off the table and we said the velocity in the downwards direction, the velocity in the horizontal direction, they're completely independent because they're at right angles to each other. That same thing happens here. However, what's interesting is if I have a wire and it's carrying current, it does produce a magnetic field. We can take a compass and we can put it around our wire and we can measure a magnetic field around it. So now we're going to have a second right-hand rule. Initially we had the direction of velocity was our thumb, our magnetic field lines, plural, were our fingers, and the force was just like pushing the palm of our hand using a positive charge. Now we're going to have a second right-hand rule, and I want you to try and think of what the right-hand rule would be, using direction of the current being thumb and my magnetic field lines being my fingers. Alright, so I grabbed a piece of PVC to represent our wire, thumb being the direction of the current, and if I hold it, to kind of relate back to what we did before, and our fingers pointed the direction of the current, or the magnetic fields, well, they're pointing right now back into the chalkboard. My fingertips are pointing back into the chalkboard. So I guess it would be backwards. Okay. Now could I also hold it like that? And now my fingers aren't pointing back into the chalkboard. My fingers are now actually pointing towards you guys. And if I rotate backwards a little bit, still my thumb points in the horizontal direction. The current's there, but now my fingertips are pointing up to the sky. So it's not necessarily going to be just pointing back into the board. What actually happens is you think about the way your fingers are rotating around. So it actually causes a magnetic field in the direction of the curve. So what you were saying was, you were saying that on the holding it, your fingers are pointing into the board, but your fingers were also on the bottom side of the wire. So let's represent that where we have all of our magnetic fields on the bottom side of the wire pointing into the board. And then when we rotated it around and I went up on top of the wire, my magnetic field lines are pointing out towards you. So I have a bunch of dots. So what this says is as it goes through it creates a loop. The magnetic field is actually in a circle around it. So here's my second question. What would be the strength of the magnetic field at this location as opposed to being at this location? Because they would both be pointing out away from the board because it's on top. But what's my strength going to be? Well, wouldn't it be just like any other example that we've had where we've been working at a distance, charges as they're farther apart, the force is less, or the electric field gets less the farther away you are. So my guess is that as the current flows through, my magnetic field, the farther away I am, would be less. And what you actually told me was you told me the relationship for this formula that we have, where we talk about the strength of the magnetic field based off of the distance away or from a wire carrying current. So we can now say that these two are inversely proportional. The farther away I go, the less magnetic field there would be. or the closer I get to my wire, the stronger the magnetic field is. Now the last part that I want to get to is I want to ask, what happens if I were to create a loop? I've got a battery set up right here where it would be producing current in this loop. Now, for simplicity, we're just going to say, what happens if I remove this? Assume that it's still carrying current. And I'm going to say that the current is in this direction. What happens if I have a loop with current? What's going to be the direction of the magnetic field? And if we go back to our right-hand rule, where I'm following my lines all the way around, I would say on the top side, it's going into the board. And then as I go through, on the inside, they would all be pointing out of the board. So as my wire is in a loop carrying current, I would create this magnetic field on the inside where I would have all my magnetic fields pointing away, and on the outside, all of them would be pointing into the board.